So this is the directed graph that we're going to create. Each edge is having source vertex and the destination vertex as each edge is directed. So these are all the edges. Now let's create this class graph, class graph, and let's have init, def init, and here we're going to pass number of vertices. Self dot v is v, and we also gonna take self dot adjacency array or adjacency dictionary. So here let's take default dict, and the default value for each key will be a list. Let's import default dict. Okay. So for each vertex we will be having a list of all the adjacent vertices. Now let's create function add edge to add edges to this graph. This is add edge, and that's gonna take u and v. U is the source vertex of this edge and v is the destination vertex for this edge. So we will add the u as a key in this default dict, and we will append the v as a value in the list that is present for that key. So default u edge u dot append v. So this will be like if you're calling add edge for 3, 2 and 3, 4, then at key 3 you will be having a list having values 2 and 4. So this is how we will be having this adjacency dictionary. So it's a relation of each vertex with all the nodes or all the vertices that it is connected to. So now let's create the main function topological sort, and let's start the main implementation. So first we're gonna take an array that will hold the integer for each vertex. So size of this array will obviously be equal to v, which is number of vertices, and initially we're gonna initialize each cell with 0. So this is the array. Now we're gonna calculate integer for each vertex, and we're gonna add that integer at the respective index in this integer array. So for each I in self.adjacency, that is for each key in self.adjacency, and for each element present in the list that is present at the for I in self.adjacency. What we will do, each time we will update the integer for that element or for that vertex j. So integer equals to the previous integer plus 1. So the number of times we encounter a vertex in these lists, that number is the integer for that vertex. So after getting integers for all the vertices, we can select the vertices that are having integer 0, right? So select vertices with integer 0, and for this we're gonna take a queue. And now let's take a for loop for I in range self.v. Here we're gonna check if the integer for that vertex is 0. If it is 0, then we're gonna add this vertex in the queue. So queue.append I. But this queue is not the container in which we are storing the result. To store the result, or to store all the vertices in linear order, we're gonna take an array, and I'm calling it linear order. So this is the array. Now we're gonna pop the vertices from Q one by one, and we're gonna put them in this array linear order. So while there are elements in Q dot pop, and let's say this is the vertex X, and now let's append X in the array linear order. Now we're gonna run a for loop. As we've added this X in linear order, we're gonna delete all the edges that are going outwards from this X, right? Or you can say that we're gonna decrement the integer for each vertex that is present in the list for X, the list for which X is the key. So all the vertices, all the adjacent vertices that are present in the list, which is the value for the key X. So decrement the integer for the current vertex. And after decrement the integer for the current vertex, we can check if the new integer for that vertex is 0 or not. So here it has lost connection with the one vertex, which is X. So that's the reason we're decrementing the integer here. Okay, so now let's check if integer of this vertex after decrementing is 0 or not. If it is 0, then we can select this vertex as well. So we're gonna add it in the queue. Append queue. Now here we're gonna take a count variable to keep track of the vertices that we have already selected. So here outside this while, let's take a variable count, and let's initialize it with 0. And here when we are selecting or when we are taking a vertex in the result, then we will increment this count. Now we're going to check for negative cycles, if there is any negative cycle present in the graph or not. So for that, we will compare C with V. We will check if the count is equal to the number of vertices or not. It must be equal to the number of vertices, but if it is not equal to number of vertices, that means the graph contains negative cycles. Dot V, and here if this is true, that means the count is not equal to number of vertices and the graph contains at least one negative cycle. And we will return from here without doing anything further, and else we will print the solution, which is stored in linear order array. So this is the implementation. Now let's take this graph and let's put it here and let's uncomment it. Now let's call topological sort on this G object, G dot topological sort. Now let's save this and let's run this program. A graph contains negative cycle, which is not true. Let's see here. Here we're comparing C with V. Here this C, this should be when we pop an element from the queue, so it must be within the while loop. Now this is the linear order that we are getting, 0, 3, 4, 1, 2. This is how we can implement topological sorting using Kahn's algorithm.